In this lesson, we'll talk more about standing waves and standing wave ratio. The objectives of this lesson are to define standing wave ratio, explain its significance for transmission line design, and calculate the standing wave ratio by using impedance values or the reflection coefficient, and to state the criterion for a perfectly matched line and describe conditions that produce an improperly matched line. As we know, when a signal is applied to a transmission line, it appears at the other end of the line sometime later because of the propagation delay. If a resistive load equal to the characteristic impedance of the line is connected at the end of the line, the signal is absorbed by the load and power is dissipated as heat. If the load is an antenna, the signal is converted to electromagnetic energy and radiated into space. When a line is not properly terminated, some of the energy is reflected from the end of the line and actually moves back up the line toward the generator. This reflected voltage adds to the forward voltage and forms a composite voltage that is distributed along the line. This pattern of voltage and its related current constitute what is called a standing wave. Standing waves are not desirable. The reflection indicates that the power produced by the generator is not totally absorbed by the load. This next figure will be used to illustrate how reflections are generated and how they contribute to the formation of standing waves. It shows how a DC pulse propagates along a transmission line made up of identical LC sections. A battery is used as the input signal along with a switch to create an on or off DC pulse. The transmission line is open at the end rather than being terminated in the characteristic impedance of the line. An open transmission line will, of course, produce a reflection and standing waves. Note that the generator has an internal impedance of Rg which is equal to the characteristic impedance of the transmission line. Assume a transmission line impedance of 75 ohms and an internal generator resistance of 75 ohms. The 10 volts supplied by the generator is therefore distributed equally across the impedance of the line and the internal resistance. Now assume that the switch is closed to connect the generator to the line. Capacitor C1 initially acts as a short circuit when the switch is closed, but soon begins to charge toward the battery voltage 2L1. As soon as the voltage at point A begins to rise, it applies a voltage to the next section of the transmission line, made up of C2 and L2. Therefore, C2 begins to charge through L2. This process continues on down the line until C4 charges through L4 and so on. Once the signal reaches the right end of the line, a reverse charging effect takes place on the capacitors from right to left. The effect is as if a signal were moving from the output back to the input. This moving charge from right to left is the reflection, or the reflected wave, and the input wave from the generator to the end of the line is the incident wave. The preceding description concerned what is known as an open circuit load. Another extreme condition is a short circuit load. Open and shorted transmission lines are sometimes used to create special effects. In practice, however, the load on a transmission line is neither infinite nor zero ohm. If the line is terminated in a resistive load equal to the characteristic impedance of the line, the sine wave signal is fully absorbed by the load. Hence, no reflection occurs. Ideally, a transmission line should be terminated in a load that has a resistive impedance equal to the characteristic impedance of the line. This is called a matched line. For example, a 50 ohm coaxial cable should be terminated with a 50 ohm resistance as shown. If the load is an antenna, then the antenna should look like a resistance of 50 ohms. When the load impedance and the characteristic impedance of the line match, the transmission goes smoothly and maximum power transfer takes place. The line can be any length. One of the key objectives in designing antenna transmission and transmission line systems is to ensure this match. A correctly terminated transmission line, therefore, is said to be flat. If the load impedance is different from the line characteristic impedance, not all the power transmitted is absorbed by the load. The power not absorbed by the load is reflected back toward the source. The power sent down the line toward the load is called the forward or incident power. The power not absorbed by the load is called the reflected power. The signal actually on a line is simply an algebraic sum of the forward and reflected signals. In case in which the mismatch between the load resistive impedance and the line impedance is great, the reflected power can be high enough to actually cause damage to the transmitter or the line itself. The condition for a short circuit is illustrated here. The graph below the transmission line shows the plot of voltage and current at each point on the line that would be generated by using the values given by a voltmeter and an ammeter moved along the line. As expected, in the case of a short at the end of the line, the voltage is zero when the current is maximum. All the power is reflected back to the generator. Looking at the plot, you can see that the voltage and the current variations distribute themselves according to the signal wavelength. The fixed pattern, which is the result of a composite of the forward and reflected signals, repeats every half wavelength. The voltage and current levels at the generator are dependent on the signal wavelength and the line length. In other words, the effects of reflected wave can simulate an open or short circuit at the generator. The illustration at the right shows the standing waves on an open circuit line. With an infinite impedance load, the voltage at the end of the line is maximum when the current is zero. All the energy is reflected, setting up the stationary pattern of voltage and current standing waves as shown. Most often, lines do not terminate in a short or open circuit. Rather, the load impedance does not exactly match the transmission line impedance. Furthermore, the load, usually an antenna, will probably have a reactive component, either inductive or capacitive, in addition to its resistance. Under these conditions, the line is said to be resonant. Such a mismatch produces standing waves, but the amplitude of these waves is lower than that of the standing waves resulting from short or open circuits. The distribution of these standing waves looks like what is shown. Note that the voltage or current never goes to zero as it does with an open or shorted line. The magnitude of standing waves on a transmission line is determined by the ratio of the maximum current to the minimum current, or the ratio of the maximum voltage to the minimum voltage along the line. These ratios are referred to as the standing wave ratio. Measuring the maximum and minimum voltage of values of voltage and current on the line is not as practical in the real world, so other ways of computing the standing wave ratio have been devised. For example, the standing wave ratio can be computed if the impedance of the transmission line and the actual impedance of the load are known. The standing wave ratio is the ratio of the load impedance to the characteristic impedance, or vice versa. And since the standing waves is really the composite of the original incident wave added to the reflected wave, the standing wave ratio can also be defined in terms of those waves. The ratio of the reflected voltage wave to the incident voltage wave is called the reflection coefficient. The standing wave ratio is obtained from the reflection coefficient according to the equation shown. If the load matches the line impedance, then the reflection coefficient is zero. The preceding formula gives a standing wave ratio of 1, as expected. With an open or shorted load, the reflection coefficient is 1. This produces a standing wave ratio of infinite. One of the best and most practical ways to compute the standing wave ratio is to measure the forward power and the reflected power. Let's try some sample problems in this lesson to measure how well you've learned. To summarize, when a line is not properly terminated, some of the energy is reflected from the end of the line and actually moves back up the line toward the generator. This pattern of voltage and its related current constitute what is called a standing wave. Ideally, a transmission line should be terminated in a load that has resistive impedance equal to the characteristic impedance of the line. This is called a matched line. However, open and shorted transmission lines are often used to create special effects. We also discussed various ways to calculate the standing wave ratio of a transmission line and define the reflection coefficient. Finally, we learned that the importance of the standing wave ratio is that it gives a relative indication of just how much power is lost in the transmission line and the generator.